Welcome to the lecture on solving radical equations. The steps that we're going to use to solve radical equations include, number one, isolating the radical. That means getting your square root or whatever your radical is on one side of the equation and all the other terms to the other side. Step two, raise both sides of the equation to the nth power, where n is the index of the radical appearing in the equation. So if we have a square root, we're going to square both sides. If we have a cube root, we're going to cube both sides, and so on. Step 3. Classify the resulting equation and solve accordingly. So you'll either end up with a linear equation, a quadratic equation, or possibly another radical equation. Step 4, and this is really important, check for extraneous solutions. A lot of times when we are solving radical equations, we will often get solutions that don't actually check back into the original problem. So you always want to check your answers. So in our first example, we have the square root of y plus 2 equals to 5. This radical is considered isolated because there are no coefficients in front of it and there are no terms added or subtracted off to the side. So we're ready to undo the square root. And what's going to undo a square root but a square? So we're going to square the left side and square the right side. We want to do it to both sides to keep the equation balanced. Now a square and a square root cancel each other out, so this left-hand side just becomes y plus 2, but we now have a new number on the right side. 5 squared is 25. Now we're going to subtract 2 from both sides, and 25 minus 2 is 23. And before we put our box around our solution, we want to do a check. So we're going to take 23 and we're going to put it back into the original equation right where that y is. So this would become square root of 23 plus 2, and we're trying to see if this really does equal 5. Well, 23 plus 2 is 25, and the square root of 25 is 5. So it does work, so 23 is our solution. Okay, let's try another example. On this one, this radical over here on the left side is not considered isolated because we have this plus 3 off to the side. So step number 1 would be to subtract that 3 over to the right side so that we get the radical by itself. Once you have the radical by yourself, then you're going to square both sides. So I'm going to square the left side and the right side. Squaring a square root cancels it out, so we get 5x minus 1 without the radical, and negative 3 quantity squared becomes 9. When I add 1 to both sides, we get 5x equals 10. Dividing by 5 gives me x equals 2. Now if I check, we're going to check back into the original equation, so we're going to be putting our 2 right here where this x is. So this will become square root of 5 times 2 minus 1 plus that 3, and we're trying to see if this is going to equal 0. 5 times 2 is 10. 10 minus 1 is 9, so we get square root of 9 plus 3. Square root of 9 is 3, and 3 plus 3 is 6, not 0. So this doesn't check out, which means that 2 is not a solution. Since it was our only possible solution and it doesn't work, we're going to write no solution for our final answer. One way that you could have noticed that that was going to happen, that we would get no solution, is back at the beginning of the problem. When we subtracted 3 right here, we ended up with square root of 5x minus 1 equals negative 3. You might have noticed from here that this is impossible. We have a positive square root on the left side. There's no way that a positive square root is going to equal a negative number. So right away you could have seen that that's not possible, so there's going to be no solutions. If you don't see that, don't worry about it. As long as you check your solution at the end, you'll see that whatever you came up with doesn't work. Okay, let's try another one. Now on this next example, we actually have 2 radicals. When you have more than one radical in the equation, it's always a good idea to try and get your radicals on opposite sides of the equal sign. So get one radical on the left side and one radical on the right side. So we have that done already for us in this example. There's no way to kind of get rid of this 6 and isolate our square root of p, because if I wanted to move the 6 to the other side, I would have to divide by it, and that would just give me a fraction over here on the right side, which makes things worse. So this is pretty much as isolated as it can get. So the only thing left to do now is to square both sides. Now when you square the left side, you are squaring not only the square root, but you're also squaring that 6. So don't forget to do that. We're going to square the right side as well. So on the left side, when I square the 6, that turns into 36. And when I square the square root, that turns into just p without the radical. On the right side, when I square my square root, I just get 30p plus 24. Now this is a linear equation because we have p to the first powers. So when we solve linear equations, we get our p's together. So I'm going to subtract 30p. So we get 6p equals 24. Divide by 6, so p equals 4. Let's do our check. I'm going to substitute in 4 right here and right here. So the left side will be 6 square root of 4. The right side will be square root of 30 times 4 plus 24. Square root of 4 turns into a 2 times the 6 makes the left side 12. On the right side, 30 times 4 is 120, plus 24 more is 144, and all of that is still under a square root, and 12 does equal the square root of 144, so this does work. So p equals 4 is our solution. If you don't want to do the check by hand, you may certainly use your calculator to verify that the left side and the right side are the same. That's perfectly okay. On the next example, we have our single radical on the left side and k plus 8 on the right. So the radical is as isolated as it can get. There's no numbers in front or off to the side. So we're ready to square both sides right away. Now the left side will be easy. When we square a square root, we just lose the radical and get 50 plus 7k. However, on the right side, here's where lots of mistakes happen. When you square the quantity k plus 8, you must FOIL. Don't forget to FOIL. Don't forget the middle term that you're going to end up with. If you don't remember how to do that, the long way would be to do k plus 8 times k plus 8 and just use your first, outer, inner, last to figure out what this is. Otherwise, you can use the square of a binomial property or square of a binomial formula, which says that the solution to this is just going to be the k squared, which is k squared, the 8 squared, which is 64, and that's always positive, and the middle term will be these two multiplied together, doubled, because we're going to end up with two of them, one from the inners and one from the outers. So k times 8 is 8k. When I double that, I get 16k, and since this was plus, my middle term is plus. So these three terms come from that square of a binomial. And if you don't remember that formula, just do it the long way using FOIL. So we squared both sides. Now if you look at this example, this equation, it's a little tougher than the last examples we've had to do because this is now a quadratic equation since I have this k squared term. So when you solve quadratics, the only way we know how to do that so far is by factoring. And in order to factor, we need to get a 0 first. So to get my 0, I'm going to subtract 50 and I'm going to subtract 7k to the other side. That way I'll get a 0 on the left side, and on the right side we'll get k squared plus 9k plus 14. And now we want to try to factor this. This is a trinomial, so we're going to use reverse FOIL. So we want two sets of parentheses. It's the slightly easier case because this leading coefficient is 1, so that forces me to have k's in the front. And I need two numbers that multiply to 14 and add to 9. That has to be 7 and 2, both of them positive. So now that we have it factored, we just set each factor to 0. So we're going to get -7 and -2. And now we want to check. So if we check, we are going to be plugging in -7 right here and right here. So if we check the -7, on the left side we're going to get square root of 50 plus 7 times -7 equals -7 plus 8. Well, -7 plus 8, that's just 1. And on the right side, 7 times -7 is -49. So we get 50 minus 49, which is square root of 1. And square root of 1 does equal 1, so -7 works. If we check -2, then we're going to get square root of 50 plus 7 times -2, and we're trying to see if that equals -2 plus 8. Well, -2 plus 8 is 6, and on the right side, 7 times -2 is minus 14. 50 minus 14 is 36, and the square root of 36 does equal 6. So both solutions work in this example. Sometimes you get both working, sometimes only one will work, and sometimes neither one will work. So you must always check both possible answers. Okay, the next two examples that we're going to look at are probably the hardest type of radical equation problems that you're going to have to do. What makes them more difficult is we have two radicals in the initial equation. So the first thing we want to do is try and isolate those radicals as much as possible, and that means that we want to get radicals on opposite sides of the equals. That's going to make the simplification much easier to do if we can separate these two radicals, get one of them on the left side and one of them on the right side. So all we have to do to move one of them over is I'm going to add the square root of m minus 2 to the right side. So this becomes square root of m plus 1 equals 1 plus square root of m minus 2. So we have those radicals on opposite sides. That's about as much isolating as we can possibly do for this problem. So we're ready to square both sides. Now the left side won't be difficult. We're squaring a square root, so those will cancel out, giving me m plus 1. However, on the right side, we have a lot of difficulty with this because remember, you must FOIL. So let's do a little scratch work over here. If we want to FOIL this, we want 1 plus square root of m minus 2 times 1 plus square root of m minus 2. That is what it means to square the quantity 1 plus square root of m minus 2. So I'm going to show you this the long way, just so you can see where all the pieces are coming from. When I FOIL, I'm going to do the first times the first, so 1 times 1 is 1. Then I'm going to do the outer times the outer. 1 times the square root of m minus 2 is just going to be the square root of m minus 2. The inner times the inner is another square root of m minus 2. And then last times last is the square root of m minus 2 times itself. In other words, the square root of m minus 2 squared. So the square and the square root cancel each other out. So for our last term, we just end up with m minus 2 without the radical. Now let's just kind of clean this up a little bit. 1 and -2 add to a -1. Then we have this plus m. And then we have these two radicals. These are considered like terms because we have both square roots and the expressions under the radicals are identical. So to add them, you add the coefficients. And this is like a 1 square root of m minus 2 plus another 1 square root of m minus 2. So it's like 1 apple plus 1 apple should give us 2 apples. So we're going to get 2 square root of m minus 2. So by FOILing this all out, here's what we ended up with. So all of that is going to go right here. So when I FOIL all this out, I'm going to end up with a -1, a plus m, and a plus 2 square root of m minus 2. So here's my new equation after squaring both sides. When we try to clean it up a little bit, you would want to isolate this radical on the right-hand side as much as possible. Notice that even after squaring both sides, we still have a radical in our equation. That's what makes this example much harder than the other ones we've done so far. usually when you square both sides, all your radicals go away. On this one, we don't get that happening because of that middle term. So when you have two radicals in the initial equation, a lot of times you're going to have to square both sides of the equation 2 times. So let's clean this up first to see what we're dealing with. I'm going to try to get the radical by itself. So let's add 1 and subtract m so that we can try and move these terms over to the left-hand side. So we'll just have 2 square root of m minus 2 by itself. Over here, the m's cancel out, and 1 plus 1 is 2. Now to further isolate my radical, I can get rid of this 2 out front by dividing. It's being multiplied by the radical, so I'm going to divide both sides by it. That'll give me square root of m minus 2 equals 1. So in this problem, we squared both sides of the equation. It got rid of most of the radicals, but we still have 1 left. Once we've isolated that leftover radical, we're going to have to square both sides again. So we're squaring the equation twice. 1 squared is 1. Square root squared cancels out, so we get m minus 2. And now this is easy to solve. We just add 2, and we get m equals 3. And then remember, we have to check. So if I plug in 3 here and here for these m's, I'm going to get square root of 3 plus 1 minus square root of 3 minus 2 equals to 1. We're trying to see if that's true. 3 plus 1 is 4. 3 minus 2 is 1. Square root of 4 becomes 2. Square root of 1 stays 1. And 2 minus 1 does equal 1. So it works. So 3 is our solution. Okay? So that's as hard as they get. When you start with 2 radicals, you want to separate the radicals, get 1 on the left side, 1 on the right side, and then you have to end up squaring both sides of the equation twice before you get rid of all your radicals. So let's try this one more time with another example. So here's another example with 2 radicals. So I kind of know in advance that I'm probably going to have to square both sides twice. The radicals are already on opposite sides of the equals. I have 1 on the left and 1 on the right. So that's about as isolated as I can make this. So we're ready to just go ahead and square the left side and square the right side. The left side, the square and the square root cancel out, giving me 2x minus 5. On the right side, we're going to either FOIL this out the long way, like we did before, or this time I'm going to show you that shortcut of using the square of a binomial formula. So the way that works is to square this binomial, we're going to square the 1, which stays 1. We're going to square the square root, which makes the square root go away, giving us just x minus 3. And that's going to be positive. And then your middle term will be these two multiplied together, doubled. Well, 1 times the square root of x minus 3 stays square root of x minus 3, and when I double it, it becomes 2 square root of x minus 3. And since we had a plus sign in the middle, our middle term is plus. So these terms here are exactly what you would get if you were to FOIL out 1 plus root x minus 3 times 1 plus root x minus 3. So you would get all of these terms if you did it the long way. Okay? So now we want to clean all this up. On the right side I have some like terms, so a 1 and a minus 3 is a negative 2. Then I have a plus x, and then I have the radical part, plus 2 square root of x minus 3. Since there's still a radical in this equation, you want to get it as isolated as you can. That means moving any other terms to the left side. So I'm going to add 2 to both sides and subtract x from both sides. So that'll make these go away. I'll have 2 square root of x minus 3 on the right side, and 2x minus x is x. Negative 5 plus 3 is negative 3. In the last example, we were able to divide both sides by 2 to further isolate the radical. I probably wouldn't want to do that here, because if I were to divide by 2, then I'm going to get some fractions on the left side, which are more difficult to deal with. So I'm just going to leave that 2 where it is and go ahead and square both sides right away. Now on the left side, make sure you FOIL. Okay, we have to FOIL this left-hand side. So when I FOIL this out, I'm going to get the x squared, the 3 squared, which is 9, and the middle term will be these two multiplied together, which is 3x doubled. So it turns into a 6x, and it's negative. So that's the left side after you FOIL. On the right side, make sure that you square not only the radical, but also the 2 that was out front. So 2 squared is 4, and when I square a square root, it goes away, so we just get x minus 3. Please make sure that you leave that wrapped in parentheses, because that 4 out front is going to need to be distributed across. So the right side becomes 4x minus 12. So now if we look at our equation, this is a quadratic equation because of that x squared. Whenever you're trying to solve a quadratic equation, you always want to get a 0 first. So I am going to subtract 4x to the left side and add 12 to the left side so that we get x squared minus 10x plus 21 equals 0. And now we should be able to factor this trinomial. Since it's got 3 terms, I'm going to use 2 sets of parentheses. I need x's in the front, and I need 2 numbers that multiply to 21 and add to negative 10. So minus 7 and minus 3. If we set each of these to 0, I'll get x equals positive 7 and x equals positive 3. Now we have to check. So if we check, let's try the 7 first. I'm going to put 7 right here and right here. We're going to get square root of 2 times 7 minus 5, and we're trying to see if that equals 1 plus square root of 7 minus 3. Well, 2 times 7 is 14. 14 minus 5 is 9, and square root of 9 is 3. So the left side is 3. On the right side, 7 minus 3 is 4. Under a square root, that becomes 2, and 2 plus 1 does equal 3. So 7 does work. If we try the other solution, 3, then we're going to need square root of 2 times 3 minus 5, and we're trying to see if that equals 1 plus square root of 3 minus 3. So 2 times 3 is 6, 6 minus 5 is 1, square root of 1 stays 1. So the left side is 1. On the right side, 3 minus 3 is 0, so this goes away, and so we get 1 equals 1, which is true, so both solutions work. Okay, that's as hard as it gets, squaring both sides twice and ending up with a quadratic equation that you have to factor. The last 2 examples that we're going to look at are a little bit different. This next one is a little different because it's a cube root on both sides instead of square roots. We have 2 radicals. I already have them isolated on opposite sides of the equals. There's nothing left I can do to kind of clean it up, so we're ready to undo those radicals right away. What makes this different from the last couple problems is that instead of squaring both sides, we're going to have to cube both sides in order to undo our cube root. So I'm just going to raise both sides to the 3rd power. A cube root cubed cancels out, so we just get this polynomial underneath the radical on the left side, and on the right side the cube root and the cube cancel out as well, so we also get our polynomial under the right side. So here's my new equation. It looks quadratic because of those y squareds, but if you notice when I try to get these y squared terms together and I subtract 3y squared, they end up canceling out on both sides. So we actually end up with a linear equation. So to solve my linear equation, I'm going to want to get y's on one side, numbers on the other side. So let's add 4y to the right side. So we get 6 equals 2y plus 8. Then we can subtract 8, get negative 2 equals 2y, and then finally divide by 2, so y equals negative 1. I will leave it to you to check that this is going to work, y equals -1, but it does check out if you plug it in for all of these y's. Okay? In the last example, this one is slightly different because if you look at this equation very carefully, there is a square root involved. However, look at the position of the variable k. The k is not under the radical. So we don't have to square both sides here, because in order to get k by itself, this square root of 2 is being multiplied by k. So all we have to do to get rid of the square root of 2 is divide by it. So it looks like a radical equation, but it really isn't. It's a linear equation because the k is already on the outside of the radical. So all I have to do is divide by square root of 2. You probably wouldn't want to leave your answer like this because it's not considered rationalized. So we would want to rationalize the denominator. To do that, you can just multiply the top and the bottom of this fraction by the denominator you're trying to get rid of. So I want to get rid of square root of 2, so I'm going to multiply by root 2 over root 2. So we're just multiplying by a fancy 1. On the top, we get 8 times root 2. We can't combine those, we just push them together. In the denominator, square root of 2 times itself is like square root of 2 squared. And when you square a square root, it goes away. So we just get the number under the radical. We just get 2. Finally, I wouldn't leave my answer like this either, because if you look at these outside numbers, 8 is divisible by 2. So this should be reduced. 8 divided by 2 is 4. The square root of 2 stays put. So k is just 4 root 2. So please be careful. Sometimes you get a trick question where the initial equation looks like a radical equation, but by the position of the variable, it's not under the radical, so you don't need to square both sides. You just divide by the coefficient, clean it up, and you're done. Alright, that concludes our lecture on solving radical equations. Good luck.